Okay, so welcome students to lecture 9. So in this lecture we'll be discussing in more details about the effective mass, right? So in the last class we have derived an expression for the effective mass. What we have what we have seen is that the effective mass can be described by the band structure, right? So that means when the electrons are moving through a periodic potential, right? The mass of the electrons are different from the free electron mass, and this mass is dependent on the band structure of the electron, right? So we defined a parameter m star, which is equal to inverse of the second derivative of energy with respect to the wave vector, right? So d2e dk2, right? So effective mass we have defined as h square times inverse of d2e dk2. So that means it is actually dependent on the curvature of the energy band, right? So this m star, this would actually describe the motion of band electrons in presence of an external field, as you have seen in the last class, right? So now once you know the effective mass, right, so we can look at the density of states, right? So the density of states, in the free electron case, we have defined as we have derived as d equal to 1 by 2 pi square times twice m by h square to the power 3 by 2 and square root of times square root of e, right? So that means density of states, and this is the case for 3 dimensions. So what we have figured out is that the density of state is directly proportional to square root of e, right? I have given a practice sheet where I have asked you to calculate actually the density of states for 2-dimensional case, right? So you can check that. Okay, so now you see that this is a free electron case, right? So I have taken the free electron mass, right? So so free electron case means this is under the Sommerfeld theory that we have discussed already in the last classes, right? So now once you know the mass of the electrons, right, when they are moving through the band through the periodic potential, right? So these are the real situations. Then one has the effective mass of the electrons, right, which we have defined just now, right? So now to take account of the band structure on the density of states, so we introduce in place of free electron mass, we introduce the effective mass here, m star. So that means what we are trying to do is that we see that the density of state for band electrons, right? So that means the electrons which are the electron states which can be explained by the block states, right? You know what a block state is. I will today deal with a little bit more about that. Right, so those electrons which can be described as the block wave functions, right? So they have their effective mass m star. Now for those electrons, if you define the density of state, the density of state will be given by 1 upon 2 pi square times twice m star divided by h square to the power 3 by 2 times square root of e. So that means what it means essentially is that now the density of state takes care of the band structure through the effective mass, right? And what we see here is that the effective mass can be different for different materials having different band structure, for example, right? So the electrons can have different masses depending on the band structure of the solid, right? So what we are saying is that the m star, or what we see here is that m star contains all the necessary information about electrons motion that is modified by the crystal potential, right? Now let us try to do this exercise. Okay, so so let us consider this band structure, right? So let us consider this as the first Brillouin zone, right? And we have two different bands here. So what we are plotting here is energy in y-axis versus k. Sorry, this should be a small k actually. K, the wave vector along the x-axis, right? So now we have a blue and red curve. So blue curve has stronger curvature, right? So therefore, since this is inverse, right, d2e dk2, inverse of this is effective mass. So therefore, the higher curvature band will be the lighter one, right? Will be the lighter mass electrons, whereas the red curve, which is the flattened one, there will be the heavy mass electrons, right? So I hope that you understand that, right? Because we have defined effective mass as this h square by d2e dk by dk2. All right. So now let us look at the density of states. Let us consider the density of states. What happens to the density of states in this, right? So now we know for fixed k space interval, right? So the number of k states, available k states, are fixed, right? So within the certain range of k values, the number of allowed k states are fixed, right? So now, considering the band structure, right, for the red curve, say, for the same width of the wave vector, your energy changes, y-axis change is smaller here in this case, right? So that means, whereas smaller than the blue curve, right? So for the same width of the k space, k values, delta k, right? So the delta E, which is in the y-axis, is much larger for the blue curve, right? Now, since the number of states are of course same for both of these, so therefore the density of states for the red curve will be much larger than the density of state for the blue curves. Is it clear to all of you? So what I'm saying is that that the density of states, in short, I'm writing DOS, density of states, is different for different bands, right? That depends on the curvature of the band. Hopefully it is clear to you, all of you, right? Okay, so once we understand the role of effective mass on the density of states, right? So we can see that the density of states can be defined by the effective mass, and the density of states will be different for different bands, and this will be all taken care of by the m star values for the different bands. Okay, the curvature of the different bands. All right. So now, once we understand that, now let us discuss about the I'll come to the concept of holes, right? So if you remember, in the last class, what I have shown, and today just at the beginning, I've told you that the effective mass is negative for the upper half of the band. Now, if you compare the band structure, which is the top curve here, E versus K, right, within the first Brillouin zone. So you see that for the lower half of the band, right, the effective mass is positive, whereas for the upper half of the band, effective mass is negative. So now we try to understand what does it mean. So there was questions, what does it mean? What does the mass of electrons negative mean? Okay, so now let us try to understand that. So we can understand that with the concept of holes. Now let us see what a hole is, right? In the context of a solid. Okay, holes, of course, you know, but in the context of solid, it has a different meaning. Okay. So now let us consider for a full ith band, sum over k equal to 0, right? So if you take the first Brillouin zone, for example, the first lowest band here, so if you see, if you sum over all the k values, right, all the allowed k values, then this will be equal to 0, right, when the band is completely full, right? So this will be non-zero when there will be some empty states. That means there will be no electrons. So let us consider this. Now, if we consider removal of, let's say, lth electron from the band, right? So we are considering a full band, and therefore sum over k, all the wave vector, equal to 0, right? Now, if we remove an electron, so that means we are creating an empty state in the band, and therefore corresponding to that state, that electron, there will be a non-zero k value, right? So non-zero k values will be allowed only if there is an empty state in the full band, completely filled band, right? So therefore in this case, now once the lth electron is removed, then you have sum over k not equal to 0. All right, so that means we can consider sum over kj. J is the number of electrons, right? Total number of electrons, where j not equal to L plus KL will be equal to 0, right? So that is the total K. Sum over Kj plus KL is the total K, right? So this is equal to 0. So therefore, Kj, sum over Kj will be equal to minus KL. So this minus KL that we are talking about as the wave vector of a hole. So hole in the sense we are talking about in the sense that this is a kind of a vacancy of an electron. Okay, so there is one less electron that we are talking about as a hole, and this less electron or vacant electron state, or a hole, or this we are calling it a hole state, right? So that is a that has the wave vector minus KL. And we are talking about, if we consider it as a hole, we are saying that, okay, this is the wave vector of the hole. Okay, so KH or K hole in this case. Okay, so now once we consider that, now let us consider that the top of a field band with energy E equal to 0. Let's consider now that a field band, right, and the top of the band let us consider is a 0. We are talking at a reference. Okay, so now if you consider t equal to 0, we are considering t equal to 0 indeed. Okay, so that means at the ground state, the top of the band, field band, the energy state at the top of the band, field band, is the Fermi energy, right? So in that Fermi energy, you know that what is the level of the Fermi energy, we have discussed that, right? A few electron volts, right? So that we are considering as 0, right? So that is, we are referencing, our reference is 0. Okay, so now if we consider this as 0, now lower down the empty band, so lower down the band, the empty state. So now we have said that we have created an empty state. Now this empty state, if it is much lower down the band, then it will, this band will be more excited. I mean, this state will be more excited, right? Right? Because at the top of the band, so if you go down lower down the band, right, and a whole state will be a more excited state. Okay, so that means the energy of a hole with respect to the top of the field band, then we can say it is a minus E of KL. Why? Because we have removed the lth electron. We are talking about this hole. So since we are considering it as 0 on the top of the band, so lower down the band, that means this is the lower energy. So this is minus E of KL. Is it clear to all of you? Okay, and then we have also defined K hole as minus KL, right? So that means we have a field band. We have removed an electron, lth electron. So due to this lth electron, there is a vacancy at that particular state. Now now because of the removal of this electron, there is that removed electron has wave vector minus KL, which we are saying that let this be as K hole, right? Wave vector of the hole. And similarly, now if we consider this topmost band, is the topmost state of the band is 0 energy equal to 0, then any state which is lower than 0 equal to 0 is minus E of KL for the lth electron, right? Okay, so now once we understand that, now let us do this. So effective mass of electrons, now this is the definition that we have done earlier, right? Now we find out what is the effective mass of holes, right? So effective mass of holes, mh star, equal to h square times inverse of d dkh deh dkh, right? So basically d2eh by dkh square, inverse of that, right? That is the definition. I mean, for electron we have defined here, and this will be just for hole. This is the same thing. I'm using suffix h for whole, right? So this is the same definition. Now this is what, now if you EH is the E whole, actually that is minus EKL, right? And K whole is minus KL. So if you put this here, you will see that MH star is equal to minus ML star. What is minus ML star? ML star is the effective mass of the Lth electron, right? So therefore this is minus of the effective mass of the Lth electron. So what we're finding is that the hole that we are defining, the effective mass of hole is equal to the minus of negative of the effective mass of the electron, Lth electron, which is the electron which has been removed from the band, creating the vacant state, hole state. Alright, so therefore what we are seeing is that negative effective mass means it's an effective mass of a hole state. So now if you look at the band structure, if you remember the band structure, so that means what we are saying is that holes in the band you find at the top, in the top part of the band, because the negative mass is there, right? Bottom part is the positive effective mass, so these are the electrons. So you have both electron states and hole state. So let me come back to this. So after we define the effective mass of electrons and holes, right? So this is what oh, I see, sorry, we have this slide here. So so that's how now we understand the effective mass of electrons and effective mass of holes. And from this lower picture, we see that the electrons are in the lower part of the band and holes are the upper part of the band, right? So that is basically what it means essentially is that when there is an empty state, right, the empty state will not start from the bottom of the band. Empty state will start from the top of the band, because you remove the electron from the top of the band, right? Okay, all right. So now, so this is all about the effective mass. So now I hope that you understand what does the negative effective mass of electron means, right? Basically, this is a mass of effective mass of holes. We are talking about a charge which is not electrons. This is holes. Okay, so now we know about the effective mass of holes. Now we find out, okay, what is the charge of that, right? What is hole actually? Right, electron, you know the charge, right? What is hole in this case? Okay, so now let us do this exercise. So now let us try to write down the group velocity of hole, right? So group velocity we defined in the last class as the 1 by h square and times gradient of the energy, right? Okay, so del E del K basically. Okay, so now in this case, this is for hole, so E energy of holes we are writing, right? And this we are defining as the is equal to BL, because here energy of hole is minus EKL, as we have just defined right here. If you consider that here, right, energy of hole is minus EKL, KL, and the derivative del E del K. Now K is also minus EK minus KL, so two negative signs get cancelled here, right? So therefore the velocity of hole and the velocity of electrons, so Lth electron. Okay, so BL stands for the Lth electron, because the Lth electron has been removed from the band, right? So this is about the velocity. Now let us consider this. We find out about the charge, right? Now, since the full band will lead to an insulating material, you understand that, right? So we have discussed that if the band is completely full, completely filled, and if you apply an electric potential, you energize the electrons. If the band is filled, there is no states available for the electrons to move to, right? So therefore the electrons don't conduct, right? So therefore this is an insulating material for a full band. I have discussed that already. Okay? So that means the current, that is minus E times Vi, which is the velocity for Lth electron, right? So and this we sum over this, so all the electrons will be equal to 0, right? Because this is insulating. We are considering a field band, remember. So then now we are separating this in terms of the j electrons and lth electron, right? So sum over this is 0. So now lth electron, remember we have removed this electron. So now sum over minus e vj, minus e is because of the charge of the electron, negative charge, right? So vj, where j not equal to l, right, is equal to minus of minus e vl star, vl vector, vl vector, right? So the velocity of the lth electron, so that means equal to plus e vh. Is it clear to you? So this is the net electron, net charge, the net current is due to the lth electron, right? Because lth electron has been removed, a whole state has been created, and this is what we are writing as Vh, right? And Bl equal to Vh we have proved earlier above. So therefore what we see here is that the negative holes have negative effective mass but positive charge, right? Is it clear? So plus E is the charge of the hole and Vh is the velocity of the holes. So what we are proving here is that we have found out a new concept of holes which have negative effective mass and positive charge. Okay. All right. So this is about the holes and their relation to the band structure. Okay, and as you understand, these holes are, as I'm saying, the holes are created by removing the electron from a field band, right? So therefore, these hole states you will find at the top of the band, right? So therefore, which means that the charge states at the top of the bands will have effective mass which will be negative, right? Okay. Okay, so I hope that you now understand the concept of holes, concept of negative effective mass, and you understand that holes have positive charge, right? Okay, so now you see we have been talking about the wave vector all along. I have introduced also its relation with the reciprocal lattice vectors, right, in the last class. So now let me discuss a bit more on this wave vector, right? So what is this k? What does this k or this wave vector represent in case of the solid with periodic potential, right? So that means we are trying to see if k, which is the momentum for free electrons in the Sommerfeld case, right? Is it the same thing when the electrons also get exposed to the periodic potential, right? So that means we are talking about free electron versus block electrons, right? So now when we are considering block theorem, we are talking about block electron, or I am talking about block theorem here because this is the wave function which defines the electrons in presence of the periodic potential, right? So the block theorem states this, right? So this is what you learned. I have discussed that already, right? So this is the wave function psi k r, which is a plane wave e to the power I k dot r times uk, right? What is uk? That's a periodic function which is the periodicity of the lattice, right? So this eigenstate psi of a one electron Hamiltonian. So Hamiltonian is given by now the kinetic energy and the potential energy, right? And this potential energy is the periodicity of the lattice. So I am writing it in general V r plus t. T is the translation vector for the Bravais lattice, right? So V r plus t equal to Vr, so that represents the periodicity of the lattice, right? So in this case, the electron state is given by the block electron, which is psi k r e to the power I k dot r uk, right? So this, which means this is a plane wave times a function which is the periodicity of the Bravais lattice. So that's what you have already known already. I'm reintroducing here. Now let us try to calculate that, right? So the momentum operator is given by minus I h cross delta, right? I h cross del. Right? So this, when it operates on the block function, right? So psi r is equal to the plane wave function e to the power I k dot r times the periodic function u r, right? And then once you do this derivative, right? So this is h cross k psi r minus this term, right? E to the power I k r I k dot r and gradient of uk, right? So which is obviously not equal to h cross k psi r, right? But you know that from the free electron case, you know P equal to h cross k, right? So we have always kinetic energy we have considered as h cross square k square by 2sm, right? Because the momentum, electron momentum is h cross k. So in the block electron, in the case of block electron, we see that these block functions, these are not the eigenstates of the momentum operator, right? So we don't get h cross k, right? We have an additional term h cross k minus e to the power I k dot r term, right? Gradient of uk. So that means what it means is basically is that k is not the physical electron momentum in a crystal, or h cross k rather is not the physical electron momentum in a crystal. For a free electron theory, yes, h cross k is the, we have considered this as the electron momentum of the crystal momentum. But for block electrons, that means when you are describing the electrons in presence of periodic potential, you are describing it with the block function, right? So these block functions, these are not the eigenstate of the momentum operator, right? So therefore we cannot say h cross k is a physical electron momentum, right? This is not a physical electron momentum. So what is h cross k? Then we define this as h cross k is a crystal momentum, right? Which takes care of the band structure. So that means we are talking about the momentum of the system as a whole. Okay, so that means momentum of the electron plus the momentum of the crystal in this case. Okay, so we are talking about the momentum of the electron as a whole. So that means electrons which experience those periodic function. So this is what is h cross k in this case, right? So therefore what we consider is that, so the k describes an electron state in a band, okay? So within a band, so it can be considered as a quantum number in that case, right? So it describes the electron states within a band. So therefore one can write the electron wave function as psi r equal to the plane wave I e to the power I k dot r uj, that is for jth band, right? So if you are considering the jth band and electron which you describe now by the band and the k. So which band? This is the jth band, so you are writing uj, right? And kth electron, so this is the ujk, and this is what is k in this case. So k is not directly the electron momentum in this case. Okay, so you need to remember that. So that means h cross k, which you have considered in Sommerfeld theory or for free electron theory, that it is the momentum of an electron in band structure. This is not the momentum of the electron, this is the momentum of the crystal system as a whole. Okay, all right. Okay, so I think these are the few major things that I wanted to discuss. So I hope that you understand now, you have some understanding about the band structure, right? We have used very simplified model, a Kronig-Penney model, and from the Kronig-Penney model we have tried to understand the band gap, right, which exists. We see that the energy bands they are increasingly wider if you go along the higher energy states. Also you see, if you have noticed, you see that the band gap is continuously reducing as you go up with the along the energy state, right? And then we have found out that there can be effective mass of electrons. So that means mass of the electrons effectively there can be negative because of the band structure effect, right? Because of the electrons, they experience the periodicity of the potential, right? So that is one thing that you have seen, and we have considered that those charges as holes. Holes. So this makes our life simpler to understand the behavior of these electrons versus hole. That means charged particles with positive mass, effective mass, and negative effective mass. So it makes our life simpler if we describe them as two identities, electron as hole. But holes are nothing but the vacancy that you create by removing the holes, removing the electrons. Okay, and then you understand that these holes have actually positive charge, right? So after that we have found out that this h cross k, which is the momentum of the electrons in free electron case. But when the electrons are associated with the kind of a baggage, right, so they are moving through this, so their effective mass is much different than the free electron mass. In that case h cross k is not the momentum of the electrons. So this is the momentum of the crystal, or called crystal momentum. Alright, so now with this, let me come to this important classification, right? So depending on the band structure, how do you classify solids in terms of metal and insulators? Now you see, if you look at ordinary materials, solids, for example, in daily life, you'll see that many of the materials, if you measure them, measure the resistance, you'll see that the resistivities are much different, right? For example, copper or gold, if you take, the resistivities are much smaller, right? Of the order of a few micro centimeter is the resistivity, right? Whereas for semiconductors, for example, or other different materials, you have resistivities of the order of 10 to the power -3 to 10 to the power 4 to 5 ohms a centimeter. So it's a large resistance range, right? And above that, that you have some other material which have extremely high resistance, right? So this I have taken from this science paper in 1998. You can check that. So that means, so how do we classify them according to the band structure? How do we try to understand their electronic behavior with respect to the band structure? Now before that, now let me ask you. So suppose I give you a piece of copper and possibly a piece of silicon, right? And I ask you to find out which is metal and which is possibly a non-metal, or an insulator, for example, right? So what you do is you measure the resistance and keep decreasing the temperature, okay, from room temperature going down towards the low temperature. So in this axis, room temperature is on the right side, low temperature is at the origin, right, on the left side. Okay, so if you measure that, you will see that the metals and semiconductors or insulators, they behave differently. Okay, so metals resistance changes, resistance changes for both of them, but for metallic case, let's say if you measure copper, you'll see that the resistance goes down, but at the absolute zero temperature or very low temperature, your resistance becomes some constant. Whereas you have other materials where the resistance keeps on increasing when you cool down the sample, right? So depending on these two properties, we call them, one is metal and another is an insulator at absolute zero temperature. This can be also a semiconductor at room temperature. Okay, so once you understand that, once you know that, okay, this is how the resistance looks like if you measure as a function of temperature, let us now try to see, can we understand them in terms of the energy bands that we have discussed so far. So what are the parameters for energy bands of metals and insulators, right? So you know metals and insulators exist, and you know how to classify them. As I have shown, you can do these measurements, then you can identify which is a metal, which is an insulator. And now, if you look at the band structure, now let me look at this. Please concentrate on the left side. On the left side, so I'm showing here is the one half of the first Brillouin zone. What I show here, I mean, these are the curves that you have already seen. So I've shown in a reduced zone scheme, and as I said that this is allowed because your K is periodic in 2 pi by A, right? So therefore, I can show it in the reduced zone scheme. So once we do that, you see that for the upper curves, upper left curves, you see there is a line, dotted line drawn at the third band, right, in between the third band. So this line represents the Fermi energy. Okay, so this represents the Fermi level, right? So what it means is that up to this EF, up to this red line, the states are filled. Beyond this, above this, the states are empty. So I have shown this as by a thick blue curve to demonstrate that these are all filled states, right? So below dotted line, the states are all filled, right? So that means this band structure shows that the topmost band is the half filled band, right? Or unfilled band. Okay, so now if it is unfilled band, so that means if I just show it in a simplified picture, I show that the lowest band on the right side, you see the lowest band is this is a box type schematic diagram. Lowest state is filled, right? Middle state is filled, so the bandwidth is completely increasing as you go up along the energy. And the third band, which is half filled, around half filled, right? So now this would mean that because it is half filled, the uppermost band is the half filled, the electrons can conduct in these states. I've discussed this, why they can conduct in this case, right? I've already discussed that. So that means this would be a case of metal, right? So this would be a band for a metal. Band structure for a metal. Whereas now if you consider the lower band, lower left one, so you see that the two bands which are filled are actually completely filled, and the third band is completely empty. Your Fermi level is lying just between the second and the third band, right? So this you see schematically, more to clarify, you see that on the right side also. So first and second bands are completely filled. Third band is completely empty because your Fermi level is somewhere in between this, right? So this means that that on the second band, which is completely filled band means it's insulator in this case, right? Because the electrons cannot, if you apply an electric field, electrons have higher energy. But if their energy is much less than the gap separation between the two bands, second and third band, there is the forbidden gap, right? Then the electrons will not have any state to go to, right? Once they get a little bit higher energy, electrons don't have states to go to move to, right? So therefore this solid will be an insulator, right? Topmost band is completely filled, completely empty, so there is no electron in this state in any case, right? So this is an insulating case. So now I can show it in a little bit different way. So this is the energy axis, and this is for t equal to 0. Right, so I am showing energy bands for metal, semiconductor, insulator. So you can classify the semiconductors and insulators at t equal to 0 depending on the band structure. So let me show this now. So for a metallic case, you know the lowest band, which we call a valence band, right? And top of this band is called the valence band edge, right? On the top band, right? So you have the Fermi level EF. right? And the bottom of the conduction band is called the conduction band edge, so EC. Okay. um, Now you can have this band. So I've shown by the band structure here, but now it's a simplistic box structure. So here you see that this is a valence band, right, and conduction band. This is another valence band, right, and conduction band is completely empty. So there is a band gap between the valence band top edge and the bottom edge of the conduction band. By the way, so the top edge of the valence band is called easily called the EV, denoted by EV, and the bottom edge of the conduction band is given by AC here. And EC minus EV is the gap EG. EG. So if the EG is small, this is called semiconductor. But for insulator, the same thing. But for insulator, EG is much larger. Okay, so you see the valence bands here. So I mean, this is how you classify the band structure at T equal to 0. Okay, so absolute zero temperature. So you can classify with the band structure. You can classify metals, semiconductor, and also insulator. Okay, so with this, I think I will stop this today. So I think this is all about the electronic structure that you need to know and which is included in the syllabus. Okay, so if there is any question, I'll be very happy to discuss with all of you. So just feel free to let me know. Maybe I can have a doubt session. It can be online to discuss with you. Okay, all right. Okay, thank you very much.